Let's clarify what casting is. Casting simply converts a value to a different data type. For example, let's say we want to work with a specific data type, in this case, a sphere. We take that data type and we make a variable using it. Now we want to assign some type of value. The problem is the value we got is not the same data type. You can see we want to work with a sphere, but we have a cube. So we need to cast or convert that cube into the sphere. If we tried working with two different data types without casting them, it's probably going to result in some kind of error, and we need to be very cautious when we do this. Once we have cast or converted the value into the data type we expect, it should clear any compatibility issues. While this is a simple example, just understand that casting can get very, very complex. Things are not always this easy. When you start into programming, virtually every language is going to have one thing in common: casting. What is casting? Well, let's say we have this little data type here, and I'm just going to say this is bright red, and it's a rectangle. That's all it is. It's just a red rectangle. We want to take this and cast it or convert it into another shape. So for example, let's say I wanted to turn that into a cloud. And then we could just, let's get this a different color here just to make it stand out. Or we wanted it to be some sort of elliptical. Give that a different color. Or, why not? Let's just take this to an extreme here. We could do it like this as well. So the point here is that when you hear the word casting, think of like a wizard casting some kind of spell. All we're doing is we're taking this object and turning it into something completely different. That's really all we're doing. Now, this doesn't always go smoothly. So for example, let's say we wanted to convert like a shape, a rectangle into a cloud. Sure. Rectangle into a circle. Sure. Rectangle into this. Sure. But could we convert that rectangle into a person? Usually not, because a person's not really a shape. A person is kind of a rather complex object. You have a brain and physiology, nervous system. Hopefully you have a brain. I had to think about that for a moment. But point being, this probably cannot easily be turned into this. And that's why casting becomes very complex, because yes, you can wave your magic wand as a wizard and cast a spell to convert a rectangle to a cloud, but it's not likely you could convert a rectangle to a person or a person into a rectangle. Now the age-old question, why? Why do we have to do this? I mean, we as developers have to do a lot of work. So let's say we have this object. It's at some memory address. We don't really care what the address is, but the point is this is a shape. This is a circle. We have a function. The function is designed to work with a square, not a circle. So we have to tell the computer, hey, take this guy and convert it into something the function can use and easily understand. Now, sometimes the computer does that for us automatically, and it does what's called an implicit conversion, which is basically a best guess. However, that can sometimes go horribly wrong. Instead of a square, it could, make like a rectangle or some other crazy shape. And we end up losing information, and it doesn't work the way we expect it to. So then we have to do what's called an explicit conversion, meaning we explicitly tell the computer, take this, convert it into this, and then use it. Let's take a look at implicit conversion. This is us just trusting C++ to, well, convert it for us. And it usually does it very poorly. Let's take a look at a very simple example here. So we're going to use a fundamental data type. We're going to say a double. And let's give it a value. And if you ever talk to a little kid, like, how old are you? They're going to say, well, I am 5 3/4 or 5 9 months old. I mean, it's very important to them that they've got that extra little bit there. And okay, well, let's see what that looks like. Our double is going to print out, you guessed it, the value exactly as we want it. Let's go ahead and run, save this. And just to prove, okay, so our double is our 5.75. That's exactly what a double is. All right, not a big deal. Now we want to work with an integer. So I'm gonna say int age equals value. What is happening here? Well, there's a lot of very complex explanations for what's going on here, but basically we are taking this double and telling C++ to implicitly convert it into an integer, which has less information. So we're going to actually lose information out of this. Let's go ahead and see that in action. I'm going to grab this, and let's call this int and age. So, pop quiz, what is it going to print out for the int? Is it going to be 5.75? Drum roll. If you said 5.75, you're very mistaken. So what happened here is C++ said, I have a double. I need to convert it to an int. They're both numbers, so I know I can convert it, but the only way I can convert this to an int is to get rid of that decimal point. And it doesn't know what to do with the remainder of the data, so it just chops it off. So is 5.75 closer to 5 or closer to 6? Those are the kind of problems you really run into. Let's talk about explicit conversion. So we're explicitly going to cast a value, and this is us telling C++ what to do. It's very similar, and we're going to, in this example, have the exact same results. I want to illustrate this just to show exactly what's going on. I took the code from the last video, 5.75, like a little kid saying, I am 5 3/4 years old. And then we're going to print that out. So it's going to print out a 5.75. We did an implicit cast where we said the age equals the value. And C++ is going to just chop off that decimal point. And then we're just going to print it out. This is an implicit conversion. We should not really trust this. Now I'm going to save and run just to show you exactly what this thing is doing. 5.75 and 5 works exactly what we thought it would. 99% of the time, that's going to work just fine. However, as a general rule of thumb, you're going to want to explicitly cast. And it looks like this. Going to give it the data type you're casting to. There's other ways of doing this. We're going to cover those as well. But basically, we're going to say our age is going to equal, and then we're going to say we want it to be this. And then we're going to take this value, which is a double. So we're going to take this double, cast it to an int, and then shove it into this variable. And then pretty much just does the same thing. The difference being now we trust this because we know what is happening. We know what is going on. We are actually controlling that process. So now we can say age, and this is an explicit conversion as opposed to our implicit conversion. Explicit conversion should be trusted because we are controlling this process. This does a few things. Now, in this example, when I run this, you're going to say, well, big deal. It's the same thing. It literally on the screen, it says 5 and 5. The difference really boils down to trust. If we are very much in control of this process, and this was something that could not be converted, it's going to throw a compiler error rather than potentially running with garbage data in it, and then our program just does some weird stuff. Again, we want to control this process. We want to explicitly tell C++, take this double, convert it to an int, shove it into this variable. Now we trust this, we are in control, and we know what to expect. I'm going to warn you right now, casting will hurt your brain. There's a billion different ways to cast. There's really not. There's only like 4 or 5. But point being, each one is slightly different for a different purpose. And what we're talking about in this video is dynamic casting. Why? Because casting is complex and we want to make it easier. Unfortunately, dynamic casting doesn't really do a good job of making it easier for us. The actual definition ripped right out of cppreference.com is the dynamic cast operator ensures that if you convert a pointer to class A to a pointer to class B, the object type of A pointed to by the former belongs to an object of type B or a class derived from B as a base class. What? That is really confusing. Boil it all down. Really what dynamic cast is attempting to do is ensure that the result of the conversion is valid and a complete object, meaning we don't want to lose information. We don't want to drop anything from this. So I've got a few classes already boiled up, ready to go. I have a car, just has a color, tires, can drive, can stop. It is a Q object. I have a race car, which is a car. So it has all of that car goodness, plus it has a supercharger and can go really fast. And then I have a feline, which is just a Q object. Notice there's no inheritance tree other than it just directly inherits Q object. It's not a car, it's not a race car, although I think most cats at 2 in the morning believe they are race cars. They are simply not, they're just cats. So we've got two functions here. We've got test drive, which will test drive a car, and race, which will take a race car and drive, stop, and go fast. Logic would say a car will work and a race car will work, but how do we put a race car into a test drive? Let's take a look and see how that works. Now, there's a bunch of different ways of doing this. I'm going to work with pointers just because I want you to really get used to the concept of pointers. So I'm going to say race car player 1 equals new race car. And spoiler alert, whenever you see the new keyword, we're doing memory management ourselves. I'm going to rely on Qt to do the heavy lifting for us, and I'm going to give it a parent. In this case, it's going to be our application. So when the application is destroyed, it will destroy this for us. I don't have to worry about memory management. All right, now we can do something like this, test drive, and we can test drive our player 1. But did you notice what's going on here? We have a race car, and we're putting it into a function that takes a car. So this is implicit conversion. Meaning we are trusting C++ to convert that for us, and it could go very badly. We don't want to do that, even though in this example, it will work. See, driving and stopping. Now, let's say we want to do this the correct way. We want to use dynamic cast here. So we're going to take, and I'm going to put a little note here, correct way. We want to make sure that we control that conversion and that we're not losing any information. So we want a car. And let's call this obj for object equals. And now I want to dynamically cast it. And it has a funny little syntax, but it's dynamic underscore cast with these brackets and then parentheses. Now, when you see these brackets, we're talking about templates. Bit more advanced than what we're talking about, but basically a template is a way of saying we're going to reuse some code. So we need to tell it specifically what we're trying to do. In this case, we want to dynamic cast into a pointer to a car. And then we're going to take our player 1. Now, whenever we do casting and you're a newbie, I tell you read it backwards. So we're going to take player 1. We want to convert it into a pointer to a car using dynamic cast and then shove it into this variable here, which is a pointer to a car. So just simply read it backwards and it makes a lot more sense. This does a few things. Using dynamic cast, we now can explicitly convert this and we trust it. And we can even test to make sure that that cast worked. So I'm going to say if obj, then we're going to go ahead and test drive using our object. What's going on here is dynamic cast is going to try to cast using this just insane logic right here. And if it can, it's going to give us a pointer. And we can use that pointer. If it cannot, it'll be a 0. So really what we're saying, if greater than 0, do this. Something like if 1. If it's 0, then it's going to just not work. So it will never be called. Let's go ahead and save run. And you see this works. This explicit conversion works as expected. Now let's take this to just some ridiculous extreme. Let's say somebody out there wants to make a feline, and this almost makes me chuckle a little bit. We're going to make a cat. I'm going to say new feline. And we want to give this a parent of our application. And I'm going to say car pointer. And let's call this cat car. I really feel like there should be things out there called cat cars. But anyways, dynamic cast. And what are we doing here? Well, we want to convert that into a pointer to a car. And we're going to use our cat. Is this even going to work? Notice how there's a warning about a potential memory leak. And there's a warning about the value starting cat car during initialization is never read. But there's no thing jumping out at us telling us, hey, you can't really convert a cat into a car. There's nothing jumping out at us doing that. So if I grab this, let's try to do this. See if this works. You notice how we have driving and stopping, first one. And then we have driving and stopping, our second one, the correct way, but no third one. It's because this is a 0. And let's go ahead and demonstrate that. I love that. Love that variable name, cat car. Instead of the Batmobile, it's the cat car. But anyways, we're just going to print that out and see what that looks like under the hood. So you can see our cat car is an object at 0, 0, meaning there's no pointer. It's simply not pointing to anything. And that's because that conversion failed. And now we have protected ourselves from potentially crashing our application. Now things are going to get a little interesting. So we're going to talk about the static cast. The static cast operator performs a non-polymorphic cast. That means it's not going to change anything. For example, it can be used to cast a base class pointer into a derived class pointer. That's interesting if you think about it. So basically, it's going to say, go out to some memory address, don't change it, but try to convert it into a derived class pointer. We're going to again use the car feline race class. Just to recap, in case you skipped the last video, the car can drive and stop. The race car inherits the car so it can drive and stop. It also has a supercharger and can go fast. The feline is just a Q object, has nothing to do with cars at all. All right. We also have two functions, test drive, which takes a car, and race, which takes a race car. Let's go down here and let's make some objects. So I'm going to say car pointer. Car equal new car. Again, you don't have to use pointers. I'm just doing it so you get used to seeing pointers. Now let's go ahead and say Q info. And I want to see what this car looks like in memory. Go ahead and save run. And sure enough, there's our car, and it's at this memory address. Let's try to use it. So I'm going to say race. And we're going to use our car. Notice how C++ is going, oh, can't do it. There's no matching function call, meaning it's not going to try to implicitly convert it for us. That's a shame. Now, we could, if we wanted to, explicitly cast it here. But notice it's still failing. Oh, that's frustrating. So let's try it this way. Magically it works. So let's see if this runs. Sure enough, it does. So it actually cast it for us. However, this is a bit dangerous because as you saw, it's easy to make mistakes. When in doubt, don't do that. Implicit simply won't work here. So what we want to do is we want to take this car and convert it into a race car. And let's call this racer. We're going to use the static cast. And we're going to convert that car. Again, if you're super confused, read it backwards. So we're going to take a car, convert it into a pointer to a race car using static cast, and put it into the variable called racer. Very simple once you put it in those terms. And then we're just going to race it. We also have the added benefit of now having a pointer, and we can simply test it before we try it. Save run. And we have successfully converted a car into a race car, and we're using it. And just to kind of illustrate this, let's grab this. I'm going to take this racer here. And you're going to see that memory address twice. You notice how it is the exact same memory address. If you see a different address, it's probably your operating system, but the main takeaway here is they're both cars. It's not changing this. It's still a car in memory, but now we can use it like a race car. That is extremely cool. This also has the added benefit of dynamic cast, which we are now testing. And what I mean by this is, let's just take this. And we're testing for completeness. So I'm going to make a feline. Remember, the cat has nothing to do with a race car, but we can make a cat car. And we're going to make a feline out of that car. Notice how it's saying static cast from car pointer to feline car. It's just smart enough to say it's just not going to work. Frustrating. Let's try it this way. Nope. Won't work. So this is the actual really cool thing here, is that it's going to stop us from trying to shoot ourselves in the foot by doing something we really shouldn't be trying to begin with. That is extremely cool. Now, the main thing you may be asking yourself is, but why can't I just do this? I want to do this because it's simpler and I see it all over the place. So we can say race car, pointer to, and it does work. It will compile and it runs. The problem we really have with this is we have no way of testing whether that conversion took place. So if the compiler did this conversion, but it just turned back raw garbage because it goofed up doing its conversion, we have no way of seeing if that actually goofed up. It's just going to try to run it with a 0 for a pointer, and then we are using nothing. That's going to be very bad. C++ is incredibly powerful. Unfortunately, it's so powerful you can do things you probably don't want to or shouldn't do, and reinterpret cast is a great example of this. Unlike static cast, but like const cast, which we haven't covered, and honestly I really don't plan on covering, the reinterpret cast expression does not compile to any CPU instructions. Wait, what? So we do something that doesn't actually compile to anything. And then they have this big red flag here, except when converting between integers and pointers or on obscure architecture where the pointer representation depends on its type. Whoa, big red flag. So what this means is the behavior is going to change depending on the situation. It is purely a compile time directive which instructs the compiler to treat the expression as if it had a new type. What? So you could do something like say, hey, take the Empire State Building and turn it into, I don't know, a helicopter. Or take the helicopter and turn it into a cat. I mean, you can do things like that with reinterpret cast. There are some rules that come into play, and it will not always succeed. And I know we've covered a lot, so quick recap. Implicit cast is C++ doing it for us. Explicit cast is us telling C++ what to do. Static cast performs a non-polymorphic cast, meaning it's not going to try to change that thing in memory. Where the dynamic cast ensures the inheritance is good, meaning you have to have some sort of inheritance tree there. Reinterpret cast takes pretty much all of that and throws it right out the window and just says, you know what, it is now this other thing just because I said so. All right, let's dive and take a look. Now, in case you skipped the other videos, we have a car, a race car, and a feline. You have just a normal car. A race car inherits the car, but goes fast. And then the feline is just a cat, which has nothing to do with any of them. Let's look at how we can cast these back and forth here. So I'm going to say, and I'm going to put some notes here because this is going to get a little confusing. We're going to create a race car. Just because we want to create a race car. I'm going to say race car, pointer to, and let's call this player 1 equals new race car. And then, of course, we want to give that the parent-child relationship. That way we don't have to worry about memory management. From here, we are going to, well, cast the race car to its base. Why? Because, well, why not? We just want to do it. So what do we need to do here? Looking at, let's scroll up here. What do we need to do here? If you said dynamic cast, because we have an inheritance tree, you're absolutely right. So let's scroll back down and let's see that in action here. So I'm gonna say car, and let's just call this object equals, and then we want a dynamic cast, and we want a car, and we're going to cast player 1. So we're going to take the race car and turn it into a car. We can do that using dynamic cast because it's going to check to make sure that there's a good inheritance tree there. We also want to check if we got an actual object, or I should say if we got an actual pointer to an object. I'm going to call that test drive. And test drive, of course, is going to take a car. So this would be a good way of testing to see if we even got this. All right, so let's go ahead and save run just to recap, show this does work. We did get it cast and we are now driving and stopping. So we're able to do that. That much is pretty obvious. Now comes things maybe we don't want to do. So we're going to cast it without changing it. Now, pop quiz, what do we need to do to cast without changing it? If you said static cast, because we're basically going to do a non-polymorphic cast, you're absolutely right. So static cast is what we need here. So we're going to say we want a race car pointer. Let's call this speedster equal static cast. And we want a pointer to a race car. And we're just going to take that object, or I should say this pointer to a car here, and that's what we're going to convert. So what I'm showing you here is that we can convert these things at will, back and forth, however we want to do. And so far, we haven't had any major issues because everything has been fairly simple. So let's go ahead and we're going to race our little speedster here. Now let's save run and let's see if this thing works. Sure enough, we can race because we've got a race car. Now we're going to dive into what I call the mouth of insanity. We are going to reinterpret as a different type. And this is a little bit brain bending here. So reinterpret as a different type here. So I'm going to say int pointer equals, and we want reinterpret cast. Now remember, reinterpret cast is going to say, okay, try to forcefully change whatever I give it into whatever I want it to be. So we're going to try and change the speedster into an integer. Now I want to qinfo that out just to demonstrate what it looks like in memory. And we're going to show the pointer. Grab this. And we also want to show what that speedster is in memory, or that race car. Save run, and let's see what this looks like here. So you can see our pointer is an integer, our race car is a race car. So we can actually reinterpret that. We have changed from a race car into an integer. That's crazy, but it worked. Now remember the little caveat we talked about, except when converting between integers and pointers or some obscure architecture. So we have probably gone into this little exception here where it's actually gone and changed it for us in the background. That is one of the little caveats here. So let's go ahead and we're just going to do the magic copy and paste, take this, and let's play around with reinterpret cast a little bit. So I'm going to say race car pointer, and let's call this my car. And we're going to reinterpret cast into a race car, and we're going to take this pointer, or this integer. We're going to just flip it back here, just to see if we can do this. And then from here, I'm going to say QInfo, my car color is my car, and we want the color. And then just to prove we can actually race with this, I'm going to say race, and we're going to race my car. I think my insurance company would probably appreciate it if I didn't actually race my car, but you know what I mean. We're just going to make sure this actually works. So what we're doing really is we're going from an integer, or I should say a pointer to an integer, to a pointer to a race car. Again, because we're working with that, it should work. Reinterpret cast is going to do that as expected. So let's try and do something like this. I'm going to grab this whole thing here, and I'm going to say feline. Remember, a feline has absolutely nothing to do with, you guessed it, race cars, but we're going to try this. So I'm going to say feline, reinterpret cast this integer into a feline. And then let's look at feline here. So a feline can meow or hiss. So we're going to try and make this thing meow or hiss here. And angry cat says, and let's grab this cat here, get rid of this, and we'll say cat dot hiss, because that's what angry cats typically do, is they hiss. Uh-oh. Notice what's going on here. Yep, we can't do this invalid binary expression because we're trying to call a function. So let's just try to call the function directly, and notice what's going on here. The IDE is not telling us, hey, this probably isn't going to work. It's just going to try it anyways. Let's go ahead and actually build this and see what happens. And we actually can build the application. But what happens when we try to run this? It actually hisses. Isn't that crazy? So what we're really doing here is we're taking this integer, which, if you remember right, what we're actually doing is taking the speedster, which was a race car. We're taking a race car and converting it into a cat. And it actually worked. That's crazy. You probably shouldn't do that because bad things may happen. If you had any sort of information in there, it's now pretty much gone. So for example, we can't say cat color. Notice there's no color in there because it's a completely different class now. Oh, that's kind of scary. So let's go back to cat and let's try meow and cat dot, I could type hiss. There we go. And let's just try doing something completely different. So we've got this car right here, and we're going to see if we can grab that. Actually, let's do race car, our player one, all the way up here. So we know this is a pointer to a race car object. So we're going to take a race car, convert it into a cat, and shove it into this pointer. Save it, build it. Absolutely no build issues. And we can now run this. So that's reinterpret cast in all of its confusion. Now, should you do this? No, absolutely not. You should not do that, because a cat and a race car are two completely different concepts and they are not interchangeable. Now, just because this on the surface appears to work, we've introduced a whole host of other issues. For example, if we were to just forget about this guy and use this cat instead, what's actually happening is we've lost all of this information in memory. It's just gone, and we have no way of getting it back unless we try to reinterpret cast, and that assumes the original memory location is still intact. Don't use reinterpret cast unless you really have no other choice, because sometimes it changes behind the scenes and you really have no control over what happens. This casting stuff gets ridiculously hard, and there are people that have heated debates about it. You're undoubtedly going to see people in the Q&A section in these videos probably saying that I'm doing it wrong, or I should have done it differently, or there's a different use case for it, and that's fine. What we've been building up to is two things. First, casting can get ridiculously complex, and Qt offers an alternative. It's called QObjectCast, and I almost always favor QObjectCast when I'm working with Qt. So what does QObjectCast do? It allows you to convert between Qt objects. And if you really dive into the documentation here, we're looking at the Qt object, and then inside of here is the QObjectCast. It basically takes it, and if it cannot convert it to another Qt object successfully, will give you a null pointer back. And the class must inherit directly or indirectly Qt object and have the Qt object macro, which we've talked about. So basically, this is only going to work with Qt technologies, but it takes away almost virtually all of this complexity. You can still use the stuff out of the standard library if you really want to, but QObjectCast is usually the way I go. So quick recap, implicit casting is C++ doing it for us. Explicit casting is us telling C++ what to do. Static casting is performing a non-polymorphic or a non-changing cast, where dynamic casting ensures that inheritance is good, and reinterpret cast is just an unholy abomination you should never really use unless you know what you're doing, because it will change from one type to another, and you could have very, very disastrous consequences there. But you can still do it if you want to, and it does actually have its uses out there. QObjectCast is what we're going to focus on, and it's going from one type of Qt object to another. So you have a solid inheritance tree. Let's go ahead and dive in and take a look. I'm going to say race car. In case you skipped these other videos, we have three classes: car, race car, and feline. Car, feline, and race car are all Qt objects, but race car inherits car. Whew. All right, mouthful. All right, so we got race car here. We're going to make a pointer, and we're going to say, let's call it my car equals new. And I want a pointer to a race car. We want that inheritance tree, so I don't have to worry about memory management. From here, I'm going to say car pointer, and let's just call this car equals, and we want a QObjectCast. And we're going to cast this into a car, a cat, car. There we go. And we do that by using QObjectCast. So we're going to take my car and just cast it into a car. Very, very simple. And then we can say, of course, my car, actually car.drive. There we go. Got them mixed around there for just a second. So both of those are now going to work. So we can use my car or car. We've cast this appropriately. Everything will just work just fine. So let's save run. And it's driving, so not a big deal. It just works. That is extremely cool. But what we've done is we've gone from a derived class to the base class. And we can do the opposite. We can go from the base to the derived class. Now, special note here, if you have any member variables, properties, things of that nature that did not exist, they will simply be the default value and they will not be set. So don't expect it to perform some wizardry on your part and set the color to like hot pink or something like that. So what we want to do here is we want to go race car. Let's call this the fast car equals, and we're going to say QObjectCast. And we want a pointer to race car. And what we need to do here is we're going to take our base and just simply convert it back to a race car. So now we can go both ways. This is extremely cool, and it's super, super easy. I mean, as you can see, we've taken a lot of the complexity out of here. And I'm going to say, I want to go fast. Save run. Let's see that in action. And there we're going fast. So let's talk about the pitfall here. The major pitfall of QObjectCast is that it does not work with, well, non-Q objects. Let's go ahead and demonstrate that. So I'm going to right-click, add new, and we're going to add a class. Let's call this dog. Base class, I'm going to leave it custom, meaning I'm not going to set a base class. I'm going to hit next and finish. Let's go ahead and go in here and add it. So we're going to say dog H and dog CPP. Now, when we flip into dog, you notice right off the bat, it's just a normal generic C++ class. There's absolutely nothing in here that even remotely points to it being a Q object because it is just a standard C++ class. There's no magic there whatsoever. I'm going to go ahead and add it. And let's go ahead and include our dog class. And let's try to convert. I'm going to say non-Qt objects. I almost said non-Qt classes, but. All right, now that we've got this, I'm going to say dog pointer. Let's call this Fido equals Q object cast. And we're going to take our race car. Why would we say race car? I don't know. Got confused there for a minute. Dog. This is what I mean by it gets super confusing. So we're going to take that, and now we're going to take our race car, our fast car. There we go. So reading it backwards, we're going to take our fast car, which is actually a race car, and try to convert it into a dog using Q object cast. And let's try this. Uh-oh, notice how we get this Qt_meta call. Whenever you see meta, remember we're talking data about data, or mock, the meta object compiler. This is basically Qt saying it has no meta information about dog because it's not a Qt object. It doesn't know what to do with it, so it's just simply going to fail. And then it's going to say here, exactly right here, it's saying there's no Q_object macro, and then at the very end here it's stating is not a member of Q object type or object type, aka dog, meaning simply cannot do this. So that is the major caveat here, is you cannot work with normal classes. However, if you really wanted to be dangerous here, you could work with one of these others and try it. General rule of thumb when I'm working with Qt is I try to almost all the time work with Qt objects because they work so seamlessly with Qt. So in most of my videos, you'll see the classes I make are Qt objects instead of standard C++ classes. There's really no problem with interrupting between the two different types of classes, whether it's just a normal class or a Qt object, but as a general rule of thumb, this is the very reason why I will almost always use a Qt object, because I can just simply use a Qt object cast to cast it when I need it.